Having applied the integration by parts method to the function y double prime minus y equals tangent t, we ended up with u1 prime is 1/2 e to the negative t tangent t, u2 prime negative 1/2 e to the t tangent t. It turns out that we aren't going to be able to find the u1 and u2 functions for this particular problem. For example, to find u1 we would have to integrate u1 prime, so we would have to do this integral. Now, how do we do an integral like this? A straightforward u substitution is clearly not going to help us. We could try integration by parts. Let's try, and of course we can't use u, let's use v and w. Let's say v is e to the negative t and w equals tangent of t. And I'm ignoring the 1/2. We can factor out the 1/2, integrate the e to the negative t tangent t, then multiply the result by 1/2 if we can find a closed form for this integral. Anyhow, this form is not going to work. V equals e to the negative t, dw equals tangent t. We could find w, we can integrate the tangent of t, it's the reciprocal of the natural log of the absolute value of the sine of t, but it isn't going to help us. You can try this breakdown and see where it leads, and it really leads nowhere. Okay, we could try v equals e to the negative t cosine, or sine t, so that dw would be, and let's see, this should have had a dt on it, dw would be 1 over cosine t dt. Again, this doesn't help. This is not going to work. You can play around with this breakdown and see. We could let v equal e to the negative t over cosine t, so that dw equals sine t dt. This is certainly integrable. We can certainly find the derivative of this, but this really leads nowhere. We could let v equal e to the negative t tangent t and dw equal dt. Not going to help us either. And the problem is that none of these breakdowns lead us to anything that really simplifies when we do an integration by parts. So I'm just going to say we can't find and if I could write a closed form solution for our function u1 of t. And the same is true for our u2. So let's try the equation y double prime minus y equals cosine of t. This is an equation we know the solution to. That particular solution is going to be y equals 1/2 cosine of t. The question is, can we find that solution using integration by parts? Using the method of variation of parameters. Applying the method, our fundamental set for this equation is e to the t, e to the negative t, and those are our functions y1 and y2. Our assumption is that there's a particular solution that's a combination of y1 and y2, sort of like a linear combination, but it's not linear because u1 and u2, rather than being constant coefficients, are functions of t. So we make that assumption, and then we skip some steps. I say then a miracle occurs. We'll fill in the steps of the miracle, not that difficult, but having made this assumption, we then know that our solutions u1 and u2 to this problem, in other words the functions u1 and u2 that lead us to the particular solution, have to satisfy this matrix equation. where y1 and y2 are the two functions in our fundamental set, and g is the right-hand side of our homogeneous equation, our non-homogeneous equation. This equation is solved by inverting the matrix in the way that we saw previously, so that we end up with u1 prime, u2 prime equal to the inverse of our fundamental matrix, our Wronskian matrix actually, multiplied by the 0g function, g being the cosine of t. So if we just plug our y1 and y2 functions into this formula here, this is what we're going to get. And I'm not going to go through the details of that. It's very straightforward. We simply do the derivatives where necessary and keep track of our signs and so forth, and we get this. And if we multiply this out, we get these two equations. Rather, we get the column matrix with these two functions, the first function being our u1 prime, the second function being our u2 prime. So applying the process, we end up with u1 prime equals e to the negative t cosine t, and u1 prime being negative 1/2 e to the t sine t. Now I really leave it up to you to do things like integration by parts, partial fractions, integrals, etc. We're not in this course focused on how to do these calculus 1 operations. However, in this case I'll do a quick integration by parts just to review the technique involved for u1 prime to find the function u1, and I simply make the note. Okay, we have integral e to the negative t cosine of t dt. Our integration by parts formula says that basically u dv, the integral of u dv, equals uv minus the integral of v du. And this is just a rearrangement of the product rule. I'm not going to explain how that's a rearrangement of the product rule, but if you see how this is a rearrangement of the product rule, you're less likely to forget it. If we let u equal, let's say, e to the negative t, and dv equals cosine of t dt, we get du equals negative e to the negative t dt, and v equals sine of t, so that this integral equals uv, which will be the e to the negative t sine t, minus the integral of v du. So that's going to be minus the integral of sine t multiplied by negative e to the negative t the negative on this will make this a plus. Without going through the details, the integral of the sine of t e to the negative t comes out like this, following very similar steps. So that if we substitute this expression here for the integral of sine of t e to the negative t, we're going to get the negative e to the negative t cosine t minus the cosine of t times the integral of the cosine of t times e to the negative t. But that, of course, is the integral we started with. And adding that term to both sides, we're going to end up with 2 times the integral of e to the negative t cosine t dt equals e to the negative t sine t minus e to the negative t cosine t, so that the integral of e to the negative t cosine t dt is 1/2 e to the negative t multiplied by sine t minus cosine t. We'll continue this solution in the next clip. Just understand that we've now found the u1 function. Having integrated the function for u1 prime, we now see that u1 is 1/2 e to the negative t times sine t minus cosine t. Just a little preview. This u1 function will now be substituted back here where it's going to be multiplied by y1. You might have been wondering how we're going to get around this exponential, e to the negative t here, in order to get back to just our known solution, which is 1/2 cosine t. This u1 function has an e to the negative t times a combination of sines and cosines. Combination of sines and cosines isn't necessarily a big problem, but this exponential seems like it would be. However, when we multiply this function by our y1 function, which is e to the t, well, the e to the t and the e to the negative t are going to multiply out to 1, and we're going to be rid of the exponentials. When we integrate the u2 prime function to get our u2 function, which will then multiply by y2, which is e to the negative t, we're going to get an e to the t in our u2 function. But it's going to multiply by the e to the negative t, again leaving us just sines and cosines.